Okay, let's turn our attention now from the wind speed chart to the actual deflection calculator. We're going to be doing a lot of writing and labeling of cells and creating of formulas. And I wanted to step back for a minute. Obviously, the big number we're looking for is that idea of how much deflection we get out of our panel system or our mullion system under a wind load. And so I want you to think about that significance of that. I'll try to mention that or punch it up in lecture. What do we consider acceptable for the kind of interior that we're designing? Is it a residence? Is it is it a condo? Is it an office building? And if so, is during a major wind event, is 3/8 of an inch a large amount of deflection? Would our clients complain about it? Would they understand that that is being done to be conservative in the way the building is engineered? So just to get us thinking about these issues in kind of a more technical way. So let's think about some of the details here. We're going to make this is basically the whole calculation. The red box is obviously the kind of the major output. It's the deflection. I just do one extra calculation to get that L over kind of calculation. So it gives us a little touchstone to what when we talk about deflections, how we can discuss them with other people, like an L over 360 is kind of an acceptable load of deflection in a floor system. People can understand that, and then they could reasonably translate that to maybe they're thinking about what would happen in a wall system. So this is the calculation system. The blue things are inputs where we are actually putting numbers in. Like I said, the red box is an output, and some of these are automatically calculated for us. And the major one here is the red box. This is the formula of deflection of a simply supported beam. So notice I'm talking about inputs and I label these in inches. It's really important that we use inches because our formula requires those inches. And we're using the panel size to determine two things. One is the length of the beam, how much of that mullion we have for deflecting. And then the other one is to figure out the tributary area that will eventually lead to how much load is on that panel system. Down here, we'll do this calculation after. We'll go through and fill this formula out. But the number, this pounds per square foot, is actually critical to coming up with the calculation for the tributary area. So this formula won't necessarily work until we've completed the whole amount of entry. So let's just start kind of looking through these things. Once again, I'm discussing this idea of panel size and reminding you that we're talking about really trying to discover this tributary area. So in lecture, we used feet, but we really need to transfer those numbers to inches. So we put in, these are input functions. We're just labeling this and creating a place to put that number in. The first calculation we do is we cube the beam length. And we're cubing that now to set us up for the formula that's going to come on later. All right, because you see we'll use that cubed function C6 in our deflection formula. And I'll just go through to the deflection formula for a minute here. And you can see that that's that length of the beam cubed all over EI of 384 EI. All right, so all of this is a coefficient times the modulus of elasticity, whether it be steel or aluminum, times the second moment area of the beam section or the column section that we're using. So let's go back to our chart. So two inputs. The first thing we do is we create in cell C6, if it's in the same corner location as you're building your spreadsheet as I am, it's equals tells it that it's a formula. In Google Docs, power written with whatever is in parentheses. So it's the cell C5 cubed. So it's the length C5 to the third power. That gives us a cube of our beam length. We're really just holding on to that number until we get down to our formula. We're doing the same thing with calculating our tributary load area. So we're taking, if we go to this one, excuse me, I didn't mean to fast forward here. If we go to this one, we're actually calculating C4 times C5, which is the dimensions of our tributary load area. But in this case, we actually have to divide it by 144 because these are in inches, and we need to, we're looking at pounds per square foot. The weight is in pounds per square foot. And so we need to change that to 144. And then we multiply that by the amount of wind load that's placed upon it. So in this case, we haven't gotten to that calculation, but it would be C15. And that's, in this case, at 100 mile an hour wind, it's 25.6 pounds per square foot. So that's our second formula. And then our actually second formula, and let me just, before we go to the third formula, let's look at the fact that we need two other pieces of data. We need we need to know what material we're using. So it's either A36 is just a common structural steel, so that's 29 million, or aluminum is 9,900,000. And you can change those numbers depending on whether you're looking at that section property or that mullion being made out of steel or aluminum. In most cases, that would be an extrusion, so it would be made out of aluminum. And then once again, we're getting from the chart that second moment of area for the C channel that we're using, or whatever shape you might pull out. And so that's a number that you just input. And then we're using all this data now in our actual calculation formula, C10. So it's that 5 times the weight times the length of the beam cubed divided by 384 times C8, which is the material we're using, the modulus of elasticity, times its section property. And when that's all multiplied out, that gives us our deflection. And then we do one more calculation. We try to do that L over calculation, and that's just a matter of taking the length of the beam and dividing it by the amount of deflection to give us our L over value. In this case, it comes out to L over 379, which is better than L360. So that's kind of, we could say this is performing it kind of like what a floor would at L over 360, which is something that architects and designers would commonly understand in discussions about that. Okay, one more thing we need is this wind speed calculator. So in this case, once again, the wind speed is an input. We're just selecting a value. We're squaring that value, so we're using the power function again. And then we're using our wind load calculation that we created in our chart before. So it's just the sum of the coefficient number that we have times C14, which is that squaring of our wind load, which we've done before in that other chart. That comes up with that number. Then that C15 number is actually used back in our tributary load, where we take our dimensions of our panel and multiply it by the load that's impressed upon it. So that'll take you a few minutes to build up and experiment with, and I hope you start experimenting with it just to see how deflection changes with the selection of deeper sections, with the change in wind speeds, so that you, I guess, can see this chart acting in a kind of a dynamic range for you to help you make evaluations. One of the critical evaluations is how deep do I want the mullion to be aesthetically, and then at that level, will it be able to limit the deflections to tolerances that I'm comfortable with as far as a designer for an interior wall system. And does it meet code, obviously, and we're hoping it for sure meets code. So the last thing we'll do is we'll look at putting this all together and how we'll report this out in something that can be submitted to the blog.